Welcome to High School Physics Explained, and today I want to briefly look at the concept of self-inductance, or what's often referred to as back EMF. So if you're watching this video and you have no understanding of a motor, or you have no understanding of the concept of electromagnetic induction, I would suggest you review this. But particularly if you're interested in what back EMF is, I'm going to go through this very quickly. So the first thing is what I have here in front is a model of how an electric motor works. So you can see I have a wire here, and these red arrows represent the direction of the current. So can you determine the direction of the rotation of this coil? Take a moment to try working it out. So let's have a look at it. So first of all, we have a current going into this side over here and out this side. Well, using your right hand palm rule, since the magnetic field lines are moving from left to right and the current is going into the page or into the board or into the video, depending on your perspective, you can see that there will be a force applied on this side that is in the downward direction. Of course, this section will receive no force whatsoever because the wire is actually parallel to the field. So this section over here being in the opposite direction in terms of current, it's pretty clear that the direction will be going upwards. And so as a result, this loop will turn in a counterclockwise or an anti-clockwise direction. So far so good. That is what a motor is all about. But now let's talk about induction. You see, the process of induction is that there needs to be a change in flux over time, and the change in flux will always be such that it opposes the motion. That's what Lenz's law is all about. So using your left hand, you should be able to determine the direction of the EMF, and by inference determine the direction of the current if there was no other current present. So let's deal with the EMF. So using your left hand rule, can you determine the direction of the EMF based on the fact that this wire is moving upward and this wire is moving downwards? So let's have a look at it. Using your left hand this time, you will notice that if this wire is moving in a downward direction, it's experiencing a changing flux, and as a result, it will produce an EMF in the direction like so. Now, that is interesting because the EMF that generates this current is in the other direction. Similarly speaking, on this side, you're going to get an EMF such that it opposes the motion in this direction. So what you in essence have is two EMFs. You have the input EMF, or voltage applied, which causes this current to flow. But as the current flows, that means we experience a force, that means it starts to rotate, that means the wire is experiencing a changing flux, and as a result there will be an oppositional EMF in the opposite direction. It's as if you've got 5 people pushing something out the door, but then we have a 6th person who basically says, oh, there is something moving towards me, I'm going to oppose the motion. But I'm only opposing the motion if those 5 people are moving the object out the door. So in other words, you might have 5 people pushing, but only while the object is moving, the other person opposes, and so you have a net force, I guess, or a net EMF of 5 minus 1 equaling 4. That's really important because that's the part that contributes to the current. So what you have is back EMF. You have obviously this concept of an EMF in the opposite direction. Can I make it absolutely clear? We do not have a back current. That is wrong. Secondly, what you need to understand is that the applied voltage is a little bit more than the actual voltage. So if your input is 12 volts, but you end up getting a negative 2 volt EMF because of the motion, your net result will be 10 volts. Now, obviously, the faster the motor increases, and that's increased by increasing the voltage, because increasing voltage increases current, and increasing current increases the motor effect, and it goes faster, well, then the rate of change of flux changes, and so that may increase as well. So you may go to 14, but then you get minus 3, and that leads us to maybe an 11 volt overall net voltage. So yes, you make it go faster, but it's not as great increase as what you put it in over here. The current will decrease as the motor as a result. Now, what does that mean? Well, the current is determined by this value over here. That's really important. So as a result, the current decreases. Lastly, I just want to talk about is the fact that many devices that are designed for this, because clearly if you need an object that has a really high torque needs, then you would need really high current. So if you put in a certain input potential difference to get that high current, then obviously you're going to get a decrease in torque because of this back EMF. So the solution is to ramp up the initial current by ramping up the initial voltage. But that must allow for the back EMF, which means if you suddenly stop the motor, then you no longer have this motion and the voltage spikes, and as a result, the current spikes. So for example, an electric drill has a particular high potential difference applied, but it is allowing for the back EMF because it's spinning really fast. So if suddenly the drill bit suddenly ceases, we suddenly have a stop in the rotation of the motor. As a result, there's no more back EMF, the voltage spikes, the current spikes, and the motor burns out as a result. And often what those devices often place in is a variable resistor that adjusts itself based on the rotation of the motion. But that's in essence why a motor can burn out, because it's allowing for back EMF. Anyway, that gives you an understanding of back EMF. I hope that helps you, and thanks for watching. Bye for now. I hope you found that video useful. And remember, like, share and subscribe. Oh, and if you have a comment or a question, or you'd like a concept for me to explain to you, please drop a comment down below. I'm Paul from High School Physics Explained. Bye for now.